Okay, so we've had a look at how we can use the Pythagorean identity and the reciprocal trig functions. I refer you to your sheet for the formulas. On the top left, you've got the Pythagorean identities. If you go a little bit further down, so there's a sign a plus or minus b, all the way down to 10 a plus or minus b. These ones are called the addition formula. Underneath that, we have sine 2a, cos 2a, tan 2a. These ones are called the double angle formula. What we're going to do is we're going to use the addition and the double angle formula to be able to do some showing.
Which one was with the double angle?
The double angles are the ones that are 2a. Yeah, it's like 2a. Alright, this is as complex as it gets. As you can see, there's two more sets of rules underneath them. They're not our concern at the moment. The application of those rules is exactly the same as what we're doing now. We're not learning about the rules, we're learning how to think about how to use the rules. And this thinking applies to across the board with all of them.
So theta can be substituted for a?
Mm-hmm. Yeah, theta, phi, whatever you want, a, b, b.
Yeah, so if we have theta as a, or
Theta, phi, or it could be delta, could be anything.
Yeah.
Could be theta and b.
Yeah.
Alright, so what we have over here is show that cos 2 theta plus 2 sine squared theta is equal to 1. Now this level of question is a little bit trickier because you're dealing with different thetas. Now whenever we deal with these, first thing I always say is flatten the fraction out as much as you can. Once you've flattened it out, so what we were doing in the last video, what you want to do is you want to deal with turning, if you see there's single thetas on the right or there's a 1 on the right, what that effectively means is you're probably going to have to reduce these to be equal to just a single theta. Or you want to speed this up so it's 2 thetas. You want them to be the same sort of thetas because you can work with that. So where I'm going to start is no fractions. So let's start with trying to turn that 2 theta into just a single theta. Now having a look at our help sheet, we've got a few things at our disposal. We've got the double angle of sine, the double angle of cosine, but there's quite a bit of it. And if we really wanted to, we could use the addition formulas, but they're not going to be that useful because you can see it's a double angle, basically. So, based on this double angle here, what sort of identity do you think we're going to use, Rowan?
The sine 2a and cos 2a.
You want to use the sine 2a? I mean, we can, and we can turn this into a 2 alpha.
Yeah.
But it'll get messy. What else could we do?
This
Cos 2a?
Yeah.
Okay, let's use the cos 2a equals cosine squared a minus sine squared a. So left hand side. And I'm going to try and pick the wrong one on purpose to show you how I would handle being wrong. Whereabouts?
Oh no, don't worry.
Yep, okay. And then let's use the first cosine one. So cos squared theta minus sine squared theta plus 2 sine squared theta. Is that cool? Okay, this one actually works. If we want to simplify this out, what can we do? Collecting like terms. Can't do anything about that. Pardon?
Can we cancel out a sine squared theta?
Yeah, cancel out a sine squared theta. This one goes in compensation of killing the 2. And then what identity can we use to simplify here?
Pythagorean.
Pythagorean. Bang.
Word.
Done. Now, is there another way we could also do this? Probably.
That's going to bring it up.
let's move this guy across. So the left-hand side is blah, blah, blah. Now, we use the first one on our formula sheet. What one do you want to use next, Lenny? The second or the third one?
Let's go to the third.
Third. Okay, let's do the substitution. Cos 2 theta is going to turn into 1 minus 2 sine, that's not good, 2 sine squared theta. And then we're going to add sine squared theta. Oh, 2 sine squared theta. Could we simplify this?
1 take 0. Oh, 1.
Wow.
Okay, the point I'm trying to make here is that you can use any number of different trig identities that all lead to the same path. Some of them won't be as apparent as the others. Some of them will make an even bigger mess and you'll get stuck.
What rule did you use for that one?
The cos 2a. Yeah, the cos 2a.
How to go negative 2 sine theta, sine squared theta.
Yeah.
How did you get that?
Oh, it was cos 2a equals 1 minus 2 sine squared a. It's the bottom one of the cos 2a's.
Oh, yeah.
Oh, right.
Yeah. But the point being made is you can sub in whatever you want. You could use whatever identity fits. But some of them might just increase complexity to the point where you don't know what's going on. In the case that happens, what I recommend is you'd say, if this didn't work here, just backtrack it and pick a different one and move on. Don't try and fix something that's clearly not working or clearly getting overcomplicated. But let's go back. How do we handle when we have a double angle in there? What do we think to do first?
Look for a formula as 2a.
Sorry?
Look for a formula with 2a.
Before that, what's your thinking about how you handle a trig identity with this? You know you deal with the fractions first, so common denominator, then make the angles what? Or make the thetas what?
The same.
Yeah, try and make the thetas common. Typically, you try and get them down to a single theta, or you try and get them down to whatever the thetas are on the right over here. So if it's a double theta here, you try and turn all of these into a double theta to get to there, and so on. So you fractions, try and make the thetas common, and then fractions again. Hopefully, when you're working on that, the complexity will lower to the point where it's apparent of what you're moving towards. We cool? All right.